Hi everyone, in this video we are going to be going through the graphs of exponential functions and just trying to show you how these things work, what they look like when we change all of the parameters that you need to know here. So let's start off with y equals a to the power of x. So you've got your most basic exponential graph here, and I'm setting a is equal to 2. If we change the value of a, and always a is positive in the models that we need to know about, you can see what happens to the graph. It gets steeper. It's difficult to know what's going on down close in the negative numbers. That red line looks like it's touching the axis, but actually it never is. So this is y equals 2 to the power of x here, and if I zoom in a bit further, you can see that the line actually doesn't touch. It's just that it's a bit of a fat line. So yeah, you've got your basic exponential graph, and if I make that 3 to the x, 4 to the x, you can see that the graph gets steeper and steeper as we get bigger and bigger. Now what happens if we change that from y equals 2 to the x to 2 to the negative x, 3 to the power of negative x, 4 to the power of negative x, 5 to the power of etc. So this is a reflection in the y-axis when you have y equals something to the power of negative x. Okay, what if we put a negative at the front before the power? So y equals negative a to the x. This now gives us a reflection in the x-axis. Okay, so there is 2 to the power of x and negative 2 to the power of x. So there's our first two reflections in the y-axis, reflection in the x-axis. Okay, this is another easy one. Y equals a to the x plus b. So now if we change the value of b, you can see what's happening to the graph. It just moves it up and down. That's all it does. It's pretty simple. Here it comes again. So here's when b is equal to 2. So this is now 2 to the power of x plus 2. You can see everything is shifted up 2. So the y-intercept used to be 1, it's now sitting there at 3. We can also go into the negatives. So 2 to the power of x minus 3 would be down here, and it would look like that. If I zoom out a bit, you'll just see that every coordinate is moved down by 3 units. Next one, y equals a to the power of x minus c. So let's look at what happens when we change the value of c. Now the graph is doing a horizontal translation, left and right. So if we have y equals a to the x minus 1, the graph has moved one place to the right. If we stop it down here, this is y equals 2, in this case a is 2, remember, 2 to the power of x plus 4. So everything in the graph has moved 4 to the left. Okay, so same transformations we've been dealing with other graphs. Alright, so we've got our vertical and our horizontal translations. Getting a bit trickier now, the dilations. Y equals k a to the x. Okay, when we put a number at the front, we get a dilation parallel to the y-axis. So the purple graph you're looking at now is y equals 2 times 2 to the power of x. I'm just going to run that, and you can see the dilation, so they're stretching out there. So if I stop it at, let's just make it 3. Yep. So this is y equals 3 times 2 to the power of x. You'll see now that instead of 1 being a y-intercept, the y-intercept is up at 3. If you pick another point out on the graph, you'll see that the y value is always 3 times that value. Okay, so when x is equal to 1, we get 2 for the red graph. When x is equal to 1, we get 6 for the purple graph. So all the coordinates are stretched out 3 times parallel to the y-axis. Okay, so that is k a to the x. And you can see what happens when we go negative here as well. So this is negative 3, 2 to the power of x. Okay, so if I make this one bigger, you can see the dilation is just, and the graph is just flipped over the x-axis. Okay, let's make this, set that back at 2. Alright, so the next one is a to the power of kx. So this one here is a dilation, but this time it's parallel to the x-axis. Okay, so we've got our values will be multiplied if we're looking in terms of the x coordinates. So let me stop it over here at, let's do 2. So this is 2. Sorry, this is 2 to the power of 2x rather than just 2 to the power of x. So if we look at our x values, the x values are going to be double what they were. So So when x equals 0, you can see they're going through the same point. When x is equal to 1, you can see the when the y value is 2, let's look at the y value of 2, you can see the orange graph is going through 1 and the red graph is going through 2. So if you look at any y value, the x values will be double. So this is a dilation parallel to the x-axis. I'll just run that again. Alright. Okay, let's look at some specific examples to put this all together. Y equals 2 to the power of x minus 2 minus 3. So let's look at what's going on. I'll just leave the basic graph of 2 to the x there in red so you can see it. When I'm looking at this one here in black, first of all, the x minus 2 in the power suggests that everything's shifted across to the right 2, and the minus 3 means everything is shifted down 3. So before, when the y-intercept was at 0, 1, now the y-intercept is at 0, negative 3. Everything has been shifted down 3, and you can see it's also been shifted across 2. Right, so that point there that we normally associate with the y-intercept would be shifted down. Would be shifted down 3, so from 1 down to negative 2 and across, just looks like it is in the sketch. Okay, next one. Negative 3 times 5 to the x minus 1. Alright, the negative at the front flips it in the x-axis. The 5 to the power of x makes this graph a lot steeper than 2 to the power of x, and the minus 1 shifts it down 1. Everything down 1. So instead of y equals 0 being the asymptote, it's shifted down to y equals negative 1. Again, if we wanted to find what the y-intercept was, put x equals 0 in there, you get negative 3 times 5 to the 0. 5 to the 0 is 1. Negative 3 times 1 is negative 3, take off 1 is negative 4. So that allows you to be accurate about what that y-intercept is there for that graph. Next one, 5 to the 2 minus x plus 1. Nasty. Because there's a negative x in the power, we've got to flip a reflection in the y-axis. So I know it was going to be flipped over and going in that direction. Because the 5 is in the base, I know it's going to be a lot steeper. And if I look at the power, I'm thinking, well, what value of x makes that 0 is 2. So this thing is shifted 2 across to the right. And it's also, with a plus 1, shifted up 1. Hence we get that black graph there. Again, putting x equals 0 in here gives me 5 squared, 25 plus 1, 26. So the y-intercept is way up here. It's difficult to see with this really big line, but the y-intercept is up here at 0 and 26. Okay, and that's what the graph looks like. Let's just look at one more here. And this is the hardest you could ever expect to get. 3 minus 5 times 2 to the power of 3x. There's a lot going on here. The minus at the front means it's going to be flipped in the x-axis. That's that minus. The 5 means it's going to be a lot steeper. That's the dilation parallel to the y-axis. So 5 times dilated to the y-axis. The 2 to the power of 3x is a dilation parallel to the x-axis as well. And the plus 3 at the front means you're going to have to shift everything up 3. So there is a whole heap of stuff going on. I can see that the asymptote is going to be y equals 3. I can work out the y-intercept again by putting x equals 0 in there. 3 minus 5 times 1 is negative 2 is going to be the y-intercept. And that's the basic shape. Some of these are really, really difficult to draw. Imagine if you had to go the other way around now, and given the graph, you have to come up with the equation. Let me do a few of those and we're done. These first ones here that we're going to look at are just ones where the base I know is going to be 3. So I know that this is going to be something like 3 to the power of x plus or minus something. So let's have a look at this. Let's just do 3 of them really quickly. So 3 to the power of x, that would normally be going like this, and it'd be going through at 1. I can see it's been shifted down 2, so I know straight away that we've got minus 2 on the end because I can see the y is equal to negative 2 is the asymptote. I can also see here has been shifted across 2, and that's it. And then we'll have that point and it's shifted down 2 because we've got this transformation here. So I'm going to adjust this one here and say that this is 3 to the x minus 2 minus 2. Let's see if that fits. So when we put x equals 0 in here, we'll get the y-intercept, and that's difficult to see, that one there. And it's also difficult to see what the x-intercept is here. So really we just need to make sure that when I substitute in an x value of 2, I should get a y value of -1. So if I check that, 3 to the power of 0 is 1, 1 minus 2 is -1, so that's right. So that equation there would fit that graph that I'm given. Next one. Straight away I know that it's going to be 3 to the -x because we've got this reflection going on in the y-axis. So I know it's going to be 3 to the -x. Again, I can see that we're going to be going down 2. So that's -2 because everything's shifted down to the asymptote there. But we're also going through the point -2, -1. So again, this is a shift, and instead of going through 0, 1, we're going back that to the left 2. So I'm guessing we could write it something like this: -x plus 2 minus 2. By writing it like this, I can clearly see that the x value of -2 makes that thing 0, so we've gone 2 to the left. Again, let me just check that's right. Let's substitute in the point -1 and -2 for x and see if that works. So -2 plus 2 is 0, 3 to the 0 is 1, 1 minus 2 is -1, so that actually works. So that could be a possibility for the equation of this graph here. The last one, y equals, in this case here, we've gone again back to the left 2, and we've also gone down 2 as well. So I think that one there we could write like that: 3 to the x plus 2 and then down 2. Now it would be very difficult for some of these to work out things like what would be a number at the start here, or if there is a number there in front of the x. They're very, very difficult questions. I think the first one is kind of reasonable. In this case here, I can see what the intercept is. I can see we're going through 0, 7. So in this case here, I'm just going to check that when x equals 0, we get 7. And in this case, 3 squared is 9 minus 2 is 7. That's correct. If that intercept up there was changed, we might have a dilation parallel to the x-axis, and we might need to, or the y-axis, so we might need to consider that number there or that number there, which you could work out. Let's say if the y-intercept was 9, it would enable you to work out what the value of k was at the front there. But I'll leave those for another time because I think we've done